Torch, Bernoulli. Description. The Torch-Bernoulli function generates a tensor of random numbers drawn from a Bernoulli distribution. The Bernoulli distribution is a discrete probability distribution that describes the probability of a single trial with only two possible outcomes: success 1 or failure 0. Inputs. P. This is a tensor of probabilities, where each element represents the probability of success 1 for the corresponding element in P. Output tensor. It can be either a single value or a tensor with the same shape as the desired output. Output tensor. A tensor of the same shape as the input P with elements randomly sampled from a Bernoulli distribution with the corresponding probabilities from P. Steps. The function generates a tensor of random numbers uniformly distributed between 0 and 1. Each element in this random tensor is then compared to the corresponding probability value in P. Input P tensor. If the random number is less than or equal to the probability, the output element is set to 1 representing success. Otherwise, the output element is set to 0 representing failure. Challenge 1. Incorrect probability input. Sample use case that resulted in challenge 1 providing a probability tensor with values outside P. Range 0, 1. Fixes to challenge 1 ensure that the input P tensor contains probability values between 0 and 1. Clamp the input tensor to the range 0, 1 using torch. Clamp 0, 1. Challenge 2. Non-tensor input. Sample use case that resulted in challenge 2 providing a non-tensor object as the P argument. Fixes to challenge 2 convert the input to a tensor using torch. Tensor. Torch, multinomial. Description. Inputs. Input A. 1D tensor of non-negative integers representing the probability distribution of A. Outcomes. The elements of this tensor must sum up to 1. Num samples an integer representing the number of samples to draw. Replacement a Boolean value indicating whether to sample with replacement true or without replacement false. If true, the same outcome can be sampled multiple times. If false, each outcome can be sampled at most once. Generator an optional random number generator. If none, the default generator is used. Output A. 1D tensor of integers representing the indices of the sampled outcomes. The length of this tensor is equal to num samples. Steps. The function generates a random sample of indices from the given probability distribution. The number of samples to draw is specified by the num samples argument. If replacement is true, the same index can be sampled multiple times. If false, each index can be sampled at most once. The generator argument allows for specifying a custom random number generator. If not provided, the default generator is used. Challenge 1. The input tensor may not sum up to 1, resulting in an error. Sample use case that resulted in challenge 1. Input torch, tensor 0.2, 0.3, 0.4. Torch, multinomial input, num samples 2. Replacement true. Fixes to challenge 1. Normalize the input tensor by dividing each element by the sum of all elements. Challenge 2. The num samples argument may be larger than the number of elements in the input tensor, resulting in an error. Sample use case that resulted in challenge 2. Input torch, tensor 0.2, 0.3, 0.4. Torch, multinomial input, num samples 5. Replacement true. Fixes to challenge 2. Ensure that the num samples argument is not greater than the length of the input tensor. Challenge 3. The replacement argument may not be a Boolean value, resulting in an error. Sample use case that resulted in challenge 3. Input torch, tensor 0.2, 0.3, 0.4. Torch. Multinomial input. Num samples 2. Replacement true. Fixes to challenge 3. Ensure that the replacement argument is either true or false. Challenge 4. The input tensor may contain negative values, resulting in an error. Sample use case that resulted in challenge 4. Input torch. Tensor 0.2. Minus 0.1. 0.4. Torch. Multinomial input. Num samples 2. Replacement true. Fixes to challenge 4. Ensure that all elements of the input tensor are non-negative. Challenge 5. The generator argument may not be a valid random number generator, resulting in an error. Sample use case that resulted in challenge 5. Input torch. Tensor 0.2. 0.3. 0.4. Torch. Multinomial input. Num samples 2. Replacement true. Generator invalid. Fixes to challenge 5. Ensure that the generator argument is either none or a valid random number generator. Torch. Normal. Description. This function draws random numbers from a normal Gaussian distribution. It is used to generate random samples that follow a bell-shaped curve, characterized by a mean and standard deviation. Inputs. Mean. This parameter determines the center of the distribution. It specifies the expected value of the random samples. STD. This parameter controls the spread of the distribution. It represents the standard deviation, which measures how much the values are dispersed around the mean. Outputs. Output. A tensor containing the randomly generated values drawn from the normal distribution. The shape of the output tensor matches the shape of the input mean tensor. Steps. Define the desired mean and standard deviation for the normal distribution. Call torch. Normal with the mean and standard deviation as arguments. The function returns a tensor with randomly generated values from the specified normal distribution. Challenges and fixes. Challenge 1. Generating values with a specific shape. Sample use case. You might need to generate random numbers with a particular shape, like a 2D matrix or a 3D tensor. Fixes. You can achieve this by providing a shape to the mean input. If the mean is a scalar, the output tensor will have the specified shape. If the mean is a tensor, the output tensor will have the same shape as the mean tensor. Challenge 2. Generating values within a specific range. Sample use case. You might want to constrain the generated values to lie within a certain interval. Fixes. You can use the torch, clam function to restrict the values after generating them. For example, torch, clam torch, normal mean, STD, min, max will limit the values to be between min and max. Challenge 3. Ensuring reproducibility. Sample use case for testing or debugging purposes. You might want to generate the same sequence of random numbers repeatedly. Fixes. You can set the random seed using torch, manual seed before calling torch, normal. This will ensure that the same sequence of random numbers is generated each time the function is called with the same seed. Torch Poisson. Description. The torch Poisson function in ptorch is used to generate a tensor of random numbers following the Poisson distribution. The Poisson distribution is a discrete probability distribution that expresses the probability of a given number of events occurring in a fixed interval of time or space if these events occur with a known average rate. Inputs. Lambda tensor containing the rate parameter lambda of the Poisson distribution. It can be a scalar or a tensor of any shape. Outputs. Output. A tensor with the same shape as lam, containing random numbers drawn from the Poisson distribution with the corresponding rates specified in lam. Steps. The torch, Poisson function takes the Lamb tensor as input, which represents the rate parameter of the Poisson distribution. For each element in Lamb, the function generates a random number following the Poisson distribution with that rate. The generated random numbers are then returned as a tensor with the same shape as Lamb. Challenges and fixes. Challenge 1: handling large rate parameters. Sample use case that resulted in challenge 1: if the rate parameter Lamb is very large, it can lead to numerical instability issues when calculating the Poisson probabilities. Fixes to challenge 1: for large rate parameters, it's recommended to use alternative methods for generating Poisson random numbers, such as the rejection sampling method. These methods can handle large rate parameters more effectively. Challenge 2: generating Poisson random numbers with a custom distribution. Sample use case that resulted in challenge 2: in some cases, you may need to generate Poisson random numbers with a custom distribution that is not directly supported by Torch Poisson. Fixes to challenge 2: you can achieve this by using the Torch distributions module in PTorch. This module provides various probability distributions, including the Poisson distribution. You can create a custom Poisson distribution object with your desired rate parameter and then use it to generate random numbers. Torch tensor Bernoulli. Description: the Bernoulli method in PTorch performs an in-place Bernoulli distribution sampling operation on a tensor. It replaces each element in the input tensor with a random sample from a Bernoulli distribution with the specified probability P. Inputs: P, a tensor of probabilities ranging from 0 to 1 for each element in the input tensor. Generator optional: a Torch generator object to use for drawing random numbers. Outputs: output: a tensor with the same shape as the input tensor, where each element is replaced with a random sample from a Bernoulli distribution with a corresponding probability in the P tensor. Self returns the input tensor with the in-place changes applied. Steps: for each element in the input tensor, a random number is generated from a uniform distribution between 0 and 1. If the generated random number is less than the corresponding probability in the P tensor, the element is replaced with 1. Otherwise, the element is replaced with 0. Challenges and fixes. Challenge 1: the P tensor must have the same shape as the input tensor or be a scalar. Sample use case that resulted in challenge 1: trying to apply Bernoulli to a tensor with shape 2. 3: using a P tensor with shape 3. Fixes to challenge 1: ensure that the P tensor has the same shape as the input tensor or is a scalar. If P is a scalar, it will be broadcasted to match the shape of the input tensor. Challenge 2: the P tensor must contain probabilities in the range 0. 1. Sample use case that resulted in challenge 2: passing a P tensor with values outside the range 0. 1. Fixes to challenge 2: ensure that the P tensor contains values within the range 0. 1. YAML. Torch tensor Cauchy. Description: the Torch tensor Cauchy method generates a tensor filled with random numbers sampled from a Cauchy distribution with the given parameters. The Cauchy distribution, also known as the Lorentz distribution, is a continuous probability distribution with a characteristic heavy tail. This means that it has a high probability of generating extreme values compared to other distributions like the normal distribution. Inputs: shape a tuple or list specifying the desired shape of the output tensor. LOC optional: the location parameter center of the distribution, if not provided, defaults to 0. Scale optional: the scale parameter of the distribution, controlling the width of the distribution. If not provided, defaults to 1. Outputs. Output a tensor filled with random numbers sampled from a Cauchy distribution with the given parameters and the specified shape. Steps. The method first creates a tensor of the specified shape. It then fills the tensor with random numbers drawn from a Cauchy distribution with the provided location and scale parameters. Challenges and fixes. Challenge 1. Unexpected shape or dimensions of the output tensor. Sample use case that resulted in challenge 1 providing an invalid or incompatible shape parameter 2. The method. Fixes to challenge 1 ensure that the provided shape parameter is a valid tuple or list representing the desired dimensions of the output tensor. Challenge 2. Invalid location or scale parameter. Sample use case that resulted in challenge 2 passing a non-numeric value or a value outside the acceptable range for the location or scale parameter. Fixes to challenge 2 provide valid numeric values for the location and scale parameters. Ensure that the scale parameter is positive. Torch tensor exponential. Description. Input 1 a p-torch tensor representing the input values. Input 2 none. Output 1 a p-torch tensor of the same size as the input tensor. Each element in the output tensor is the exponential of the corresponding element in the input tensor. Output 2 none. Step 1 for each element in the input tensor. Calculate its exponential value a raised to the power of that element. Step 2. Store the calculated exponential values in a new tensor with the same size as the input tensor. Challenge 1. Handling very large or very small input values. When dealing with input values that are extremely large, the exponential function can result in an overflow, producing an INF infinity value. Conversely, for extremely small input values, the exponential function can lead to an underflow, resulting in a zero value. In such scenarios, it is important to ensure that the input values are within a reasonable range for the exponential function. This can be achieved by applying techniques like scaling or clipping the input values to prevent overflows or underflows. Challenge 2. Not a number values in the input tensor. If the input tensor contains non-values, the exponential function will also produce non-values in the output tensor. Before applying the exponential function, it is advisable to handle any non-values present in the input tensor. This can be done by replacing them with a suitable substitute value or by selectively excluding them from the calculation. Torch tensor geometric. Description. Tensor Geometric is a p-torch extension library for deep learning on graphs. It provides a unified framework for graph neural networks (GNNs) and includes a range of pre-built models, datasets, and utilities. Tensor Geometric allows researchers and developers to easily implement and experiment with GNNs for various tasks like node classification, graph classification, and link prediction. Input data in the form of a p-torch geometric data object. This object represents a graph and contains information about nodes, edges, features, and labels. Model. A p-torch geometric GNN model instance. Model outputs. These outputs can vary depending on the task and model used. For example, in node classification, the output would be a tensor of predicted class labels for each node. Loss. The loss value, calculated by comparing the model's predictions with the ground truth labels. Data preprocessing. The input data is processed and transformed into a format suitable for the GNN model. This might involve converting the data into the p-torch geometric data object, creating adjacency matrices, and extracting node and edge features. Model training. The GNN model is trained on the processed data using an optimizer and loss function. This involves iteratively feeding the data to the model, calculating the loss, and updating the model's parameters to minimize the loss. Model inference. Once the model is trained, it can be used to make predictions on new data. This involves feeding the new data to the trained model and obtaining predictions. Challenge 1. Overfitting to small datasets. When training on small datasets, the model can overfit to the training data and perform poorly on unseen data. Sample use case that resulted in Challenge 1. Training a GNN on a small graph dataset with a limited number of nodes and edges. Fixes to Challenge 1. Regularization techniques. L1 and L2 regularization can help prevent overfitting by penalizing large model parameters. Dropout. Randomly dropping out neurons during training can help prevent co-adaptation of neurons. Early stopping. Monitor the model's performance on a validation set and stop training when performance starts to decrease. Challenge 2. Handling large graphs. Training GNNs on large graphs can be computationally expensive and memory intensive. Sample use case that resulted in Challenge 2. Training a GNN on a social network graph with millions of nodes and edges. Fixes to Challenge 2. Mini batching. Divide the data into smaller batches and train the model on each batch separately. Graph partitioning. Partition the graph into smaller subgraphs and train the model on each subgraph independently. Graph sampling. Sample a subset of nodes and edges from the graph and train the model on this sampled subgraph. Challenge 3. Choosing the right GNN architecture. Selecting the appropriate GNN architecture for a specific task can be challenging. Sample use case that resulted in Challenge 3. Building a GNN for a node classification task where the graph structure is complex. Fixes to Challenge 3. Experimentation. Try different GNN architectures and compare their performance on the task. Understanding the data. Analyze the graph structure and node features to choose a GNN architecture that is suitable for the specific task. Transfer learning. Fine-tune a pre-trained GNN model on a similar task. Challenge 4. Interpreting GNN predictions. Understanding why a GNN makes a particular prediction can be challenging. Sample use case that resulted in Challenge 4. Trying to explain why a GNN classified a node as belonging to a specific class. Fixes to Challenge 4. Visualization. Visualize the GNN's attention weights or feature activations to understand how the model is making decisions. Feature importance. Identify the most important features for the model's predictions. Gradient-based explanations. Use gradient-based techniques to explain the model's predictions. Torch tensor lognormal. Description. The lognormal function generates a tensor of random numbers drawn from a log-normal distribution. This distribution is characterized by the natural logarithm of the random variable being normally distributed. Inputs. Mean. This is a tensor representing the mean of the underlying normal distribution. It should be a float tensor with the same shape as the desired output tensor or a scalar float. This parameter determines the central tendency of the distribution. STD. This is a tensor representing the standard deviation of the underlying normal distribution. Similar to mean. It should be a float tensor with the same shape as the desired output tensor or a scalar float. It controls the spread of the distribution. Output. This is a tensor of the same shape as the input mean tensor, populated with random numbers drawn from the log-normal distribution defined by the given mean and STD. Steps. Generating random numbers internally. The function draws random numbers from a standard normal distribution mean 0. STD1. Applying log-normal transformation, the generated random numbers are then transformed using PE. Formula XP mean STD normal random numbers, where express is the exponential function. Normal random numbers are the randomly generated numbers, and mean and STD are the provided inputs. Invalid input types. Sample use case that resulted in challenge 1 trying to provide a tensor with integer data type for mean or STD. Ensure that mean and STD are float tensors or scalar floats. Casting the input tensors to float before passing them to lognormal can resolve this issue. Dimension mismatch. Sample use case that resulted in challenge 2 providing mean and STD tensors with different shapes. Fixes to challenge 2. The shapes of mean and STD tensors should match. If you need to generate a tensor with a specific shape, make sure the inputs have the same shape as the desired output. Negative standard deviation. Sample use case that resulted in challenge 3 providing a negative value for STD. Fixes to challenge 3. Standard deviation cannot be negative. Ensure that STD is a positive value or 0. The lognormal function might raise an error if STD is negative. Overflow. Sample use case that resulted in challenge 4 using very large values for mean or STD. Fixes to challenge 4 using very large values for mean or STD can lead to numerical overflow during the exponential transformation. This can be addressed by rescaling the input values or by using a suitable data type for the output tensor that can handle larger numbers. YAML. Torch tensor normal. Description. The torch normal function is an in-place function that fills a tensor with random numbers drawn from a normal distribution. It operates directly on the input tensor, modifying its contents. This makes it efficient for generating random data within an existing tensor without creating a new one. Inputs. Mean. A tensor representing the mean of the normal distribution. It must have the same shape as the output tensor or be broadcastable to the output tensor's shape. STD. A tensor representing the standard deviation of the normal distribution. It must have the same shape as the output tensor or be broadcastable to the output tensor's shape. Generator. Optional and optional torch. Generator object for generating random numbers. If not specified, it uses the default generator. Outputs. Output. The input tensor filled with random numbers drawn from a normal distribution. Steps. Determine the output tensor's shape. Generate random numbers from a normal distribution with the specified mean and standard deviation. Fill the input tensor with the generated random numbers. Challenges and fixes. Challenge 1. Input tensor shape mismatch. If the input tensor's shape does not match the shape of the mean or standard deviation tensors, or if they are not broadcastable, a runtime error will occur. Sample use case that resulted in challenge 1. Python. Import torch. Tensor torch. 1s 2. 3. Mean torch. 0s 3. STD torch. 1s 3. Torch. Normal tensor. Mean. STD. Fixes to challenge 1. Ensure that the shapes of all input tensors are compatible for broadcasting or explicitly reshape the tensors to match. Challenge 2. Input tensor data type mismatch. The input tensor, mean, and standard deviation tensors should have the same data type. If not, a runtime error may occur. Sample use case that resulted in challenge 2. Python. Import torch. Tensor torch. 1s 2. 3. D-type torch. Float. Mean torch. 0s 2. 3. D-type torch.int. STD torch. 1s 2. 3. D-type torch.int. Torch. Normal tensor. Mean. STD. Fixes to challenge 2. Ensure that all input tensors have the same data type. Convert them to a compatible type if necessary. Torch tensor random. Description. The torch tensor random method is used to fill a tensor with random numbers from a uniform distribution. It modifies the tensor in place, meaning it changes the values directly within the existing tensor. Inputs. From optional lower bound of the uniform distribution inclusive, if not specified, the default is 0, to optional upper bound of the uniform distribution exclusive, if not specified, the default is 1. Outputs. Self the tensor itself, filled with random numbers. Steps. The method generates random numbers from a uniform distribution between the specified from and to. Values inclusive for from, exclusive for to. These random numbers are then used to fill the tensor in place. Overwriting any existing values. Challenges and fixes. Challenge 1. Overwriting existing tensor data. Sample use case when you have a tensor that already contains important data. Calling random on it will overwrite that data with random values. Fixes. Use torch rand to create a new tensor with random values instead of modifying an existing one. Create a copy of the tensor using tensor clone before applying random to avoid modifying the original data. Challenge 2. Using incorrect bounds for the uniform distribution. Sample use case providing incorrect from or to values might result in unexpected random numbers, or a distribution that doesn't meet your needs. Fixes. Carefully consider the desired range for your random numbers and provide accurate from and to values. Double-check the documentation and examples to understand the inclusive and exclusive nature of the bounds. Challenge 3. Using random on a tensor with a specific data type. Sample use case if the tensor is of a specific data type, such as torch.int or torch bool. Random might not produce the desired results. Fixes. Use torch randint for integer tensors. Use torch Bernoulli for Boolean tensors. Ensure the data type is compatible with the random number generation method you choose. Torch tensor uniform. Description. The torch tensor uniform method fills a tensor with random numbers from a uniform distribution. It modifies the tensor in place. Inputs. From the lower bound of the uniform distribution. It must be a float. If not provided, defaults to 0. To the upper bound of the uniform distribution. It must be a float. If not provided, defaults to 1. Outputs. Self the tensor filled with random numbers from the uniform distribution. Steps. The method generates random numbers from the uniform distribution with the specified lower and upper bounds. These random numbers are then used to fill the tensor in place. Challenges and fixes. Challenge 1. The bounds specified for the uniform distribution are not float values. Sample use case tensor. Uniform 0. 10. Fixes ensure that both the from and to arguments are float values. For example, tensor uniform 0.0. 10.0. Challenge 2. The lower bound is greater than or equal to the upper bound. Sample use case tensor uniform 10. 5. Fixes ensure that the lower bound is strictly less than the upper bound. For example, tensor uniform 5. 10. Torch quasi-random Sobol engine. Description. The Sobol engine class in PTorch is a generator for quasi-random Sobol sequences. These sequences are designed to be more evenly distributed than random numbers, which can improve the accuracy and convergence rate of numerical integration and other stochastic simulations. Inputs. Dimension. This integer represents the number of dimensions for the Sobal sequence. Each point in the sequence will have dimension coordinates. Scramble. This Boolean argument default false determines whether to use scrambled Sobal sequences. Scrambled sequences have a more random appearance, which can be beneficial in certain applications. Seed. An optional integer that controls the starting point of the sequence. This allows for reproducibility. Outputs. A p-torch tensor containing the generated Sobal points. The shape of the tensor is n samples. Dimension, where n samples is the desired number of samples. Steps. Initialization. Create a Sobal engine object, specifying the dimension. Scramble flag. And optional seed. Sample generation. Call the draw method on the Sobal engine object to generate a specified number of Sobal points. Challenges and fixes. Challenge 1. Generating a large number of Sobal points can be memory intensive. Sample use case that resulted in challenge 1. A user needs to generate 1 million Sobal points in 100 dimensions, which requires a significant amount of memory. Fixes to challenge 1. Consider using a generator approach to generate points in batches, rather than generating all points at once. This can be more memory efficient, especially for high-dimensional problems. Challenge 2. Ensuring reproducibility when using scrambled Sobal sequences. Sample use case that resulted in challenge 2. A user wants to generate the same scrambled Sobal sequence multiple times for a specific experiment. Fixes to challenge 2. While scrambled Sobal sequences are designed to appear more random, they are still deterministic. To guarantee reproducibility, use the same seed value when initializing the Sobal engine.